Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So in the last lecture, I introduced the basic ideas of optical gain and how a laser cavity is constructed and how lasing occurs, right? We discussed the fundamental aspects of it. Now in this lecture I want to move a little bit ahead, and then I want to discuss about nanoscale lasing. Okay. So I think I've shown this particular slide already in my introduction video to the course. I said that if you have there is a big mismatch between the size of the electrical components or electrical transistors and the optical devices like a laser, a modulator and so on. So I showed this picture and said that, so this is the IC with lots of transistors, and this is just a single laser, a modulator, a few modulators and detectors, right? So I also said that, okay, there is this huge opportunity for disruptive research in integrating these optoelectronic devices. And I showed you, this is an example from Intel, this is from Marvel. So a lot of interesting work that's being done, okay? And this is actually very recent work. So now I want to ask a question. Why should we miniaturize a laser? Okay. It might seem very natural, given that we have seen so much of benefits when we miniaturize the electronic devices, namely the MOSFETs. There was a lot of improvement in terms of the price, the performance, and so on. So we should do the same thing with optical devices. Yeah, that's one argument. But I just want to give you a more detailed argument. So right now we know that the communication, long distance communication, is all with an optical fiber. In fact, if you look at any supercomputer, the connections between the various racks in a supercomputer is already with a fiber. So typically what they would do is, have a laser driver, basically a chip or a board, which essentially has these VCSELs integrated on it, and then you modulate these lasers depending on how much information what information you want to transmit, and all of that is transmitted on an optical fiber, and you can have a receiver circuit on the other end, which is the opposite. So this is already happening. Now, if you want to miniaturize that and actually bring it on the chip, a possible approach could be to integrate them on the chip. Okay, so you'll have to VCSELs. I'll introduce what is a VCSEL, but in a moment. But these are reasonably large devices. Now, so I have to miniaturize my laser and also the detectors, and then you'll also have some things like a waveguide on a chip and so on. Right. The important, I think, driving factor in this regard is the energy. Okay. Always when we miniaturize the electronic devices, we have seen that the amount of power consumption reduces, or at least reasonably it remains the same, while the number of operations that we can do increases. Okay, so right now a typical amount of energy that is spent in performing a floating point operation is floating point operation is about 0.01 to 0.05 picojoules per bit. So it's a small amount of energy that is required to actually perform the operation, the logic. But if you look at the energy that is required to transport the data, because a computing device actually just performs a computation, but it has to interact with the external world. So if you're trying to transport this data, it turns out that the amount of energy required to transport this information or a bit is actually much, much larger, up to almost 200 times larger than the energy required to perform the computation itself. So in this case, some number, I've taken this data from this presentation by Benner at one of these conferences. You can look at this reference, you'll find it. So the amount of energy is 200 times larger if you're trying to transmit the information on a card, maybe a few inches. Okay, but the moment you want to transport the data over large distances, like between maybe meter scale, the amount of energy required would be even more larger, like almost like 2000x larger. So this is a large amount of energy, and we would like to minimize that so that we can transmit information efficiently. Why would we want to do that? Well, it turns out that now, I think in 2022, One of the first demonstration of an exascale computer was done. So essentially it can perform 10 power 18 operations per second. So there are problems like weather modeling and mapping the brain and so on, so which require huge computational resources, and you have computers which are doing that. So when you have such a large amount of computational capacity, you also have to bring in information to the computer on that scale. So there's a tremendous amount of requirement to transport this data, and that itself requires huge budgets. Somewhere I've seen a number, I don't remember where exactly, but up to tens of megawatts of power is required just to transport the data. So it's a significant thing. So, and if you're able to reduce the amount of energy required for transport, that's a big addition, or it's an improvement in technology. So what prevents us from reducing the amount required for transmitting the data? One of the challenges in that regard is that the traditional lasers, I showed you one laser in the last lecture, wherein I said that there is this gain medium, a double heterostructure, and then the facets are cleaved, right? That is called as an edge emitting laser because it emits from the side, and that's a standard laser in the past. In the 1960s it was invented. So now if you look at that laser, the threshold for lasing is typically in the order of milliwatts. So the threshold is reasonably high, all right? And if you look at that sort of a threshold, and if you look at, let's say you want to transmit 10 gigabits per second data rate, it'll roughly translate to about picojoules per bit. So since the laser threshold is high, there's nothing you can do about it. You have to expend that much of energy to even just generate and transmit the data, right? There's nothing, even if you have a perfect interconnect, you would still have to expend that much of energy because just the threshold is high, all right? So, but is it really required to spend that much of energy in actually, going beyond the threshold of a laser? Well, it turns out that if you look at a photodetector, it can actually detect pulses with as low energy as 0.2 femtojoules. So it's a very, very small amount of energy that is required to actually detect pulses if you have even a thermal noise limited photodetector. But because the laser has a very high threshold, we are forced to transmit energy at that range, and we would like to minimize that. So what stops us actually from reducing the threshold? The reason threshold is high is that the lasers are substantially large, tens to hundreds of micron size. When you have a large area device, we will have to create population over all of that region, much larger active region, and so we have to expend that much of energy. That's one reason why the threshold is large. And so the immediate question will be, can we shrink the size of the laser so that we don't have to pump a large volume? We pump a small region of space, and that should provide us lasing if it's possible, right? So that's a natural question to ask, and that is what I'm illustrating here schematically. So think of the original laser was this you had this double heterostructure with two edges. Can I make it smaller? Can I even do away with the mirrors and actually confine my electromagnetic energy in a nano disk like this? We have seen when we studied the mirror resonances, we saw that just a semiconductor disk itself can confine can confine energy, and the Q factor can be reasonably large. So if you have a large disk, typically on the sizes of, I would call this as maybe micro disk, it's been shown that you can have very good confinement of electromagnetic energy in that, and it can actually exhibit lasing. But the moment you try to go to nanoscale, like, for example, we went to nano antennas, semiconductor nano antennas I mentioned when we did the Mie theory calculations of it. So if you have a nano antenna, there's a problem. The reason is we have understood the fundamental diffraction limit of light, right? So if you have a particular medium of refractive index n, and the size of the antenna is smaller than that, we automatically saw that the wave is going to leak out into the surrounding environment, and that is what is schematically shown here. So if the wave is leaking out, that means the cavity is not really that good. Okay, so how can we miniaturize these devices? Okay, so this is an active area of research, and a lot of work has been done over the last 20 years, I would say, 20 to 30 years. So I would just try to give you a snapshot of it. Okay, so with our understanding now, you know why it's a problem to miniaturize these antennas, right? And now, so I'll give you a snapshot so that you appreciate the research. That's it. Okay, my goal is not really to explain each and every aspect of it. That would really be an intensive course in itself, just the design of the nano lasers. So I will not go into that. I'll just give you a snapshot. All right. So this is a very quick overview of how the nanoscale lasers evolved over the last 30 to 40 years. Okay. So the original devices that were initially fabricated was, these edge emitting lasers. So you had the double heterostructure, and from the side you have the emission. So the facet here on the side, this acts as a mirror, and light goes back and forth between that, and then you have emission. So these edge emitting devices were actually demonstrated way back in 1960s, and they work very well. One of the important figure of merits in this case is the volume of the device divided by the wavelength, whole cube. So the lambda cube is roughly how much the wavelength is, right? So how much can you confine? How much smaller than the light is the volume of the laser. So if you look at these edge emitting devices, the EEL means edge emitting lasers. This is when you have these edge emitting lasers, you see that they perform reasonably well, but their volume is large. So this is the range over which you can have lasing. Okay, these are the traditional cavities. And quickly after that, in about a decade or so, by 1978, a new type of design was implemented that is called as a VCSEL. So this is basically, a VCSEL means vertical cavity surface emitting laser. So if you look at the traditional laser, the cavity actually is formed by the mirrors on the edges here, and then there has to be a certain volume for the lasing to happen. So that was not very efficient, and the size was large. So scientists invented the idea of a vertical cavity. So what they did was they would put a mirror in the bottom and the top, and then the gain medium in between. So it's also interesting how these mirrors are constructed. These are actually what are called as distributed Bragg mirrors, DBRs. Using photonic crystal ideas, we can actually design these structures. So it's simply alternating layers of different dielectric constants, and so that at a particular point we saw that there's a peak reflection. So you put two different distributed Bragg reflectors that way, and in between that you put a gain medium here, schematically shown by this here, and then you have a lasing cavity. And now instead of light emitting out from the sideways, which is difficult to couple, light is emitted on the top, and now this device size can be much smaller than the traditional laser. So the light is being emitted outward like this. And if you compare to the original edge emitting lasers, the vertical cavity lasers are actually much smaller, about an order of magnitude or so smaller. Okay, so this is the VCSEL that was done in 1978, so already 4 decades back, very old technology. But now the idea is, can we miniaturize this further? So one of the landmarks in that direction is a microdisc laser, which was demonstrated in the early 1990s. So instead of this sort of a cavity, take a simple disc. Okay, and in this form, in this case, this is actually supported by a small pyramid bottom below. So there is a disc which is holding on top, sitting on top of a pyramid. And so when you have such a disc, which is a gain medium with some the diameter of the disc would be something like 5 to 10 microns of that scale. So you have what are known as whispering gallery modes. Basically, the light keeps going around in circles in that micro disc. So this is a microdisc laser, and in that light keeps traveling in circles. So essentially it constructively interferes at a particular wavelength, and you have lasing. So when you come to this, you see that with a microdisc, the size of the laser has dramatically reduced compared to the VCSEL. So this is one of the key factors, kind of one of the key achievements in early 90s. And later on, even the ideas of photonic crystals. We talked about the photonic crystals, wherein you have these arrays of holes exhibiting photonic band gaps. So if you have such a structure exhibiting a photonic band gap, so I can create a small region of space which is having a gain medium, and all around it I make it a photonic band gap. So in that case, light cannot escape anywhere else, and it is forced to be confined to a small volume. And using that, it is shown that you can actually have lasing. Okay. One of the problems here is that even though the gain area is very small, the surrounding cavity turns out to be in the range of tens of microns. So overall, still the size of the laser is of the similar scale as the microdisc laser. So these are all this is another achievement that happened around the turn of the century. After that, in the early 2000s, there was a lot of effort try to actually grow nanowires. And nanowires means just a disk of maybe few microns, less than a micron or so, and then you actually grow a vertical nanowire, and in that the cavity is formed. So you can have again edge emitting devices in nanowires, and you can have lasing from them as well. So if you notice, all three of these structures here, both the micro disc laser, the photonic crystal cavity laser, and the nanowire laser, the sizes are relatively same. So for about almost, I would say 2 decades, if the micro disc is early 90s, so till about I think late 2000s, at least 2 decades, there's not much of progress in miniaturizing the laser. The reason for that was all of these are essentially constructed out of what we call as dielectric materials. And we know that if you have a dielectric material, you can't miniaturize below a certain point, right? Below a certain size, if you try to miniaturize the dielectric structure, the light is not confined very well. So they are limited by the diffraction limit. And to overcome that, one of the landmark achievements was actually demonstration of what is known as a plasmonic laser or a spacer. This was done in the year 2009, so just over 10 years back. So the basic idea for a spacer was actually proposed by Mark Stockman and Bergman in 2003, I believe. And later on in 2009, a group of people, a group of various research groups actually, one from Purdue, one from I think Berkeley, and another from I'm not sure, I forgot where it is, but then 3 different groups in almost the same year they demonstrated lasing, which actually where the cavity is actually sub diffraction limit, below the diffraction limit. So in the case of a spacer or a plasmonic laser, so these arrows represent where the antenna, where the volumes of the devices that were demonstrated. But in principle, we already know that if you have a plasmonic nanostructure, we can actually confine light much below the diffraction limit. Right? We know that the K vector for the SPP, surface plasmon, polariton, or even surface plasmon is much greater than the wave vector for a free space. So because of that, you can actually confine light in much smaller dimensions. And in principle, it looks possible that if you have a plasmonic laser, you can actually go to even smaller dimensions. Okay, and if you have a much smaller confinement of energy, definitely your lasing would be better. Right, the lasing threshold will be lower. So this was the overall picture how evolution happened. Evolution of the lasers happened right from 1960s to 2009. So and this is just the to give you a flavor of what this was. The plasmonic nano lasers. So as I said, there was one group led by Professor Noginov in Norfolk and Professor Shalaib at Purdue and a few others. So wherein they have taken a gold particle, nanoparticle, and then coated that with a silica shell, and the silica shell actually was embedded with a dye. So the dye essentially acted like a gain medium, and the gold core acted like the source of surface plasmons. And when you have such a core shell nanostructure, this is what we call as core shell nanostructure. They saw that the lasing. They saw that the wavelength of the emitted light actually is very narrow, indicating that there is lasing. And immediately after that, it's just the same around this next issue of the Nature journal here. Another group by another group led by Shang Zhang from Berkeley, they demonstrated a lasing phenomena using a nanowire. So in this case, what they did was they took a metal, coated it with a dielectric, and put a nanowire on top. The nanowire is a semiconductor. You pump it, it creates the gain. And then at the interface between, in the gap between the nanowire and the metal, there's a gap plasmon mode which is excited, and that actually the gain amplifies the gap plasmon mode, and you have lasing from this tiny region in between the separation of the cadmium sulfide nanowire and the metal in the bottom. So the thickness of the dielectric, the MgF2 magnesium fluoride film here determines how well the mode is confined, and they showed that if you have such a structure, you can actually have lasing, and from a very low volume. Okay, one important feature that I think we should appreciate, I think so far all the demonstrations of nano lasers, all of them, nearly all of them, have confinement of electromagnetic energy in only one of the dimensions. Really, 3-dimensional confinement. This is one example where there is 3-dimensional confinement, but still this is a nanoparticles embedded in a matrix. So if you have a structure like this, here there's a confinement in the vertical direction, but along the nanowire it's large. So we still don't have a very good laser where all the 3 dimensions, in all the 3 dimensions you confine the electromagnetic energy, and that would be an interesting thing that has to be done. Okay, so this is one particular case, and after this, again, there is a whole zoo of demonstrations, I would say, various structures that people have proposed, starting from these initial demonstrations, where people have tried various configurations to demonstrate nanoscale lasing. So on the top you have this old microdisc and nano, and later on this was followed by metal dielectric structures, where they combine the metal structure to provide the confinement and the dielectric to provide the gain. So a whole range of lasers were demonstrated. And if you want to know the details, you can go and look at this particular review, which summarizes all of it, where they're taken from, some of the key highlights. And one of the key, I think I like this demonstration a lot, so I am emphasizing this here. So this is from Arizona State, I believe. So wherein they have taken the semiconductor, and you see now we understand what this is, right? We have a heterostructure. So you have indium phosphide substrate, and then there is different doping, different layers that are grown on top of it. And then here is my gain medium. Sorry, the gain medium should be this. Oh no, N-type. Okay, N-type. So the gain medium, I think, should be here in between. So wherein the size of this structure is 500 nanometers on the right. So you see that. So it's larger than the wavelength of light, but the interesting thing is here it's electrically driven. So you have a bottom contact. So the electrons or holes, the holes are injected from here, and the electrons are injected from the top contact here, and then they recombine in this region and then emit light. So this is an electrically driven laser. The previous 2 demonstrations here, these are actually optically pumped. Optically pumped are nice, but eventually if you want to integrate it in terms of technology, you would want to have electrically pumped laser. So even though this is not sub-wavelength, I like it because it's one of the first demonstrations of electrically pumped lasing from metal dielectric structures. This was, I think, done in 2007. So when you increase the current that is applied to this, you see that initially at low currents below the threshold, you have a broad emission. That's what is shown here. The blue is probably low, it's definitely low current below the threshold. And as you increase the amount of current that is applied, you see that there is a sharp peak that comes out. And this sharp peak is what is known as a lasing peak. So generally when you have below the threshold, you have only spontaneous emission, amplified spontaneous emission. So there's a broad emission over a range of wavelengths where you can have gain. But when you cross the threshold, one particular mode becomes dominant, and all the electromagnetic energy is actually emitted into that particular mode. And the signature, the change of the emission width, FWHM, the full width half maximum of the emission, from a broad emission into a narrow one, is one of the signatures of lasing. Okay, and it turns out that, of course, even just what is lasing and what is a threshold of a laser itself is quite a matter of debate. So initially, people would demonstrate this sort of a peak, which is narrow. That was accepted initially, but then over time, people realized that that is not itself enough. We have to look at other properties of laser, and I'll just show you one more in the next lecture. But yeah, so this was the way the field has evolved over time. And lastly, this was the metal dielectric structures, but there's also an increased emphasis on trying to find alternative cavity structures to actually get lasing. Okay, so I said that dielectric structures are, they cannot confine energy smaller than the wavelength, but can we have alternative structures which can actually provide low threshold lasing? So there's a lot of work that is going on in what we can call as arrays of nanoparticles. All right. So this is a brief overview of nanoscale lasers. Mind you, I just only talked about the lasers, but in effect, you actually need other devices like the modulators and the detectors and so on also have to be miniaturized. And all of that is an intense area of research across the world. And there's a lot of excitement around this. But in this course, I think we will not really have the time to cover that. So I'll stop here for now, and I'll see you in the next lecture. Thank you very much.